So welcome you all for the new lecture. So in this lecture we are going to see about the electrodynamics and electromagnetic waves. So this is the fifth unit. In this the topic is dynamically induced EMF. So for this we are considering two metal rails. Okay, so these two are made up of metals. This R1 and R2 they are made up of metals, and it is placed over a magnetic field. So this X which is mentioning the field, okay, so which are perpendicular to the plane of the uh, okay, plane of the screen. So here these two rails are connected to a galvanometer. So it will show some small, even though if there is any small movement of sorry, any small amount of current is flowing, so we can identify using this galvanometer. And here you can see a movable conductor that is mentioned as M. So that is moving from a position of A to B. Okay, and the whole length or the distance between these two rails are given by L. Okay, right. So while moving this movable conductor from A to B, what happens means there is an increase in flux that takes place inside this loop. Which is the loop here? This is A prime, B prime. So this is the loop. So within this, the flux will increase. So here you can see um, the area swept by A prime, B prime. Area swept by A prime, B prime is given by L into dx. So it's just like a rectangle, and the length is given as L, and the thickness is given as or the distance moved is given by dx. So the flux linked with that particular loop is given by B into L into dx. Okay, so in general we know that the electromotive force, that is EMF, is given by the rate of change of flux d phi by dt. Here this is again equal to B into L, and we can use this as the change in the value with respect to the movement of this conductor. Okay, so that is change in x, so dx. So dx by dt, bl into dx by dt. Here we are substituting v instead of dx by dt. Now we will get em of E is equal to b into l into v. Okay, so from this equation we can understand that emf depends on the flux density, and second one is length, and this is velocity. Yes, so this is dx by dt, so rate of change of displacement. So the movement from a position A to B, this displaced, so rate of change of displacement is given by v, that is velocity. So this gives the dynamically induced EMF. Now let us move on to the Lenz's law. Okay, so first you look at this diagram. So you consider this as figure number A, and this is B, and this is C. So first let us see this figure number C. So here you are considering a loop of wire. So this is the wire loop. You are moving a bar magnet towards the loop. Okay, you are moving the bar magnet towards the loop. So because of this, that means it is pushed towards. So what happens means the flux through the loop is increasing, whereas it induces a current too. Okay, so induced current will happen there. And what is happening there? Because of this induced current in the loop, that current direction is such that the loop's magnetic the loop's magnetic field opposes the motion. Opposes the motion. So since these two poles repel each other, okay, the pole of this magnet and the pole of this loop repel each other. Whereas in the other case, that is from figure B, you can see that the bar magnet is moved downwards, that is pulled. Okay. Now what happened? The opposite process will take place. The flux through the loop is decreasing here. Flux is decreasing. So this is the observation we can make here. And this also results in an induced current. So that is flowing in a direction. So such that the magnetic field opposes the motion. But here they are in the unlike poles, so they will attract each other. So the opposite effect happen here. So from this we can identify that whether it is pulled or pushed, so the opposite effect is takes place in this loop. So that is the observation we can make. Now let us see this, the main diagram, that is figure number A. Now what is happening? We are giving some power supply to this first circuit. So that is circuit A. So there is a coil wounded over something, and another one circuit, that is B. Okay. So it is connected to an ammeter. So what will happen? Well, the power supply is given, the conductor, that automatically it induce some EMF here, it produce some magnetic field, and in turn it produce some EMF. So it is induced to this B, okay, induced to this B. So because of this, what happened means, the original magnetic field set up by the increasing current in circuit A, so that will be strengthened. Okay. So the induced EMF, so here induced EMF, so in this equation, this from A, it induce an EMF to this B. When there is induced EMF, the current will be increased, and in turn the flux also increased. But actually what happened means, this is impossible, because this is like a chain process. It can increases endlessly. So theoretically we can say, but this is impossible because of the effect is in the opposite direction, just like the previous two case. Okay, so when the magnet is moved, so here it is like act like a magnet, since it is and it is moved towards the B, so it induces EMF and it produce current, but it will be opposed. Okay, so from this we can understand that according to Lenz's law, according to the Lenz's law, the effect opposes the cause. Okay, so the effect induced EMF is given by this circuit, and but the direction is in the opposite direction. It is opposed in the opposite direction to that of A. Okay, so these are some key points here. So that's all about this Lenz's law. So the effect opposes the cause. So just relate with the a magnet movement to the loop. Okay, whether it is pulled down or pushed up. Uh, so just the opposite. It is effect is takes place here. So it is related to the these two circuits A and B. Okay, that's all for this lecture now. See you in another video. Thank you. Bye.